Hey, Ali, ready to tackle these linear algebra notes?
As red as I'll ever be. It's that lecture on solving linear equations. Let's see, we're looking at a system of simultaneous linear equations.
Exactly, and the main equation we're focusing on is ax equals b. The notes define what each part means. A is an m by n matrix that's given, and b is a given vector in f to the m. Our goal is to find x, an unknown vector in f to the n.
Okay, so we have this equation, ax equals b. Why are we trying to solve it? What's the point?
That's what the next page is about. The notes lay out the three key questions we need to answer. First, when does a solution even exist?
Why is that the first question? Can't we just assume a solution exists?
Not always. That's why we have to figure out the conditions for a solution to exist. The second question is, if a solution does exist, is it unique or are there infinitely many?
Oh, I remember this from high school math. Sometimes a system of equations has one answer, no answers, or infinite answers. Is this the same thing?
It's the same idea, just with matrices. And finally, the third question is, how do we describe all the solutions?
Got it. Let's dig in. I need some intuition for this.
Okay, the notes start with the foundational concepts. The first one is that linear maps preserve subspaces. So let's say we have a linear map, F, from vector space V to vector space W. The notes show an illustration of this.
What's a linear map again? Is that the same as a linear transformation?
Yes, a linear map is a function between two vector spaces that preserves vector addition and scalar multiplication. The next page shows a theorem related to this. Theorem 1 states that if V' is a subspace of V, then the image of V', which is denoted as f of V', is a subspace of W.
The image, is that like the range? So the set of all possible outputs?
Exactly. And the proof on this page shows how we can check this using the subspace criteria. It's a subspace because it contains the zero vector and is closed under linear combinations. The next foundation is about spanning sets and dimension. Theorem 2 says that if a set of vectors, v1, v2, up to vr, generates a subspace V', then their images, f of v1, f of v2 to f of vr, will generate the image of that subspace, f of V'.
Why is that true?
The proof explains it. Any vector in V' can be written as a linear combination of v1 up to vr. Since f is a linear map, the image of that vector will be a linear combination of the images f of v1, f of v2 up to f of vr. So the images generate the image space. The notes also say that if V' is finite dimensional, its image f of V' is also finite dimensional. And the dimension of the image will be less than or equal to the dimension of the original subspace, dim V' greater than or equal to dim f of V'.
Okay, so we know that the linear map's output is also a subspace, and its dimension is at most the dimension of the input space. How does this help us with our original problem?
This brings us back to our first key question. Theorem 3 gives us the answer. The equation ax equals b has solutions if and only if b is in the image of the linear map defined by a. The notes denote this as b belongs to f of a of f to the n.
If and only if. That means it's a two-way street. A solution exists if b is in the image, and if b is in the image, a solution exists. What does that actually mean, though?
The notes elaborate on this. The equation ax equals b can be rewritten as a linear combination of the columns of A. So, saying that b is in the image of the map, f of a of f to the n, is the same as saying that b can be written as a linear combination of the columns of A.
That makes so much more sense. We're just checking if b is in the span of the columns.
Exactly. Now, to answer the second question about uniqueness, we need another foundation, inverse images. Theorem 4 says that if we have a linear map F from V to W, and W' is a subspace of W, then the inverse image of W', which is denoted as F to the -1 of W', is a subspace of V.
Let me see if I get this. We have a linear map from V to W again. We pick a subspace in the destination space W'. The inverse image, f to the -1 of W', is the set of all vectors in V that get mapped into W'. And the theorem says that this set, f to the negative 1 of w prime, is also a subspace. Why is that?
The proof on the next page shows how it satisfies the subspace criteria. The proof is similar to the last one. We just need to check the two subspace criteria. First, since w prime is a subspace, it contains the zero vector. We know f of 0v equals 0w. Since the 0w is in w prime, it means the zero vector of v, 0v, is in the inverse image, f to the negative 1 of w prime.
Okay, and for the second part about linear combinations.
Take any two vectors in the inverse image, v1 and v2, and any scalars a and b. The goal is to show that their linear combination, av1 plus bv2, is also in the inverse image. Since v1 and v2 are in the inverse image, their images, f of v1 and f of v2, must be in the subspace w prime. Since w prime is a subspace, any linear combination of f of v1 and f of v2 will also be in w prime. Because f is a linear map, a f of v1 plus b f of v2 is the same as f of av1 plus bv2. Since this expression is in w prime, it means our original linear combination, av1 plus bv2, must be in the inverse image, f to the negative 1 of w prime. Now, there's a special case of the inverse image called the kernel. The kernel is the inverse image of the zero vector. The notes define it as k of f equals v in v, where f of v equals 0w.
So the kernel is a set of all vectors that get mapped to the zero vector.
Correct. Now, let's connect this back to our equation. If we look at the linear map determined by our matrix A, its kernel is the solution space of the homogeneous equation ax equals 0. The dimension of the kernel, dim kernel f of A, tells us the degrees of freedom of the solution.
Okay, so we figured out when a solution exists, but how does the kernel tell us how many solutions there are?
That brings us to our second key question. Theorem 5 gives us the answer. If B is in the image of the linear map and we have a specific solution, say x equals v naught, then any other solution can be expressed as x equals v naught plus v, where v is any vector from the kernel.
Wait, why is that true?
The proof shows us why. If both x and v naught are solutions to ax equals b, then their difference, ax minus v naught, is equal to ax minus av naught, which is b minus b, or the zero vector. This means that the difference, x minus v naught, is in the kernel. So x is just the specific solution v naught plus some vector from the kernel. So the kernel's dimension tells us how many solutions there are. A dimension of 0 means one unique solution, and a dimension greater than 0 means infinitely many solutions. And that's how we describe the solutions, which was the third question. If we have a basis for the kernel, say u1, u2 to ur, then the general solution is the specific solution, v naught, plus a linear combination of those basis vectors, x equals v naught plus c1 u1 plus plus cr ur. The dimension of the kernel, r, is the degrees of freedom of the solution.
The final page is a great summary. Let me read them out. The notes say, when does a solution exist? Ax equals b has solutions if and only if b belongs to f of a of f to the n, which means b is a linear combination of the columns of A. The next point is, how many solutions are there? If by mention kernel of A is 0, the solution is unique. Otherwise, infinitely many solutions exist. And finally, how can we describe them? Dimension kernel A is the degrees of freedom of the solution.
This actually makes sense now. I feel like I have a much better handle on it.
Me too. Let's grab some coffee before we start the next topic.
Good idea. This was a lot to take in.